I'd like to thank the organizers for invitation. I think in the last few years I think the field of quantum gases continue to expand rapidly in all directions, and in the last few years we were, I think, continually dazzled by the physics of strong interactions and the synthetic gauge fields, the mesoscopic physics emerging in quantum systems, and also the developments of very powerful atom microscopes. Indeed, we have lots of progress, but there is a nagging question all the time. We have strong interacting system, but we do not have a system that really truly manifests strong correlations. In particular, the kind of quantum Hall states, and that is a question that has been addressed a few years after coatoms, and then I'm just absolutely delighted to see that now we have a chance to really coming back in a very strong way for various reasons. So what I'm going to do today is to hope to use this opportunity to communicate to the two communities the issues that we have here, and then where we are, and then I would like to also propose a way to overcome some of the intrinsic difficulties of getting the latest quantum Hall states. And let me first mention that this is the current platforms for addressing quantum Hall states. I think the earliest platform, and I think it's still remaining, is the rotating gas. And then we have rotated the single component Bose gas, and we can get vortex lattice. And Eric Cornell's team is the only one so far that has reached the lowest Landau level. However, but still, to go even you are in the lowest Landau level for bosons, to get into quantum Hall state is still difficult, and there are some intrinsic reasons for it. And for fermions, and again, with the experiments rotating, very beautiful rotating gas experiments on the superfluid phase, but there's no so far. I mean, we are not yet reached the lowest Landau level. Then there's a considerable progress in synthetic gauge field of all kinds of things that many of which you have heard of in the last few days, which I have to, I'm not going to repeat. And there are many beautiful experiments, and the goal is really to go to a lattice where you have one or less than one atom per size, and then do correlate the physics. And there are it seems that, I mean, if I turn to speakers today, Monica and I think Tillman also thinks that the prospects are good, that we could get to those regimes, because I thought we'll be looking very much forward to that. And I think there is a very promising directions, and to using small rotating clusters. And for the condensed matter, for the coatom people, I think they might be interested to know that the most powerful calculations in condensed matter through exact diagonalizations can only handle, I think, less than 20 particles. And then if we can, and these clusters can range from a few to 50 particles, then in that case, then one can have a calibration of this quantum simulator for small clusters, and then go to big clusters, and then to understand its effects. And there's, well, sorry, I forgot to clean up my slide. And my talk will be my talk will be mostly focused on the first platform. There's a tremendous amount of physics, and I like to just discuss this for a reason, for a very simple reason. The reason is that this is the most faithful representation for the electron problem, and I think has been discussed earlier today that the Hamiltonian for the rotating gas in harmonic trap is this is a dot p. I mean, there's a momentum, and there's so this is a L dot z term, so L sub z times omega term, and then so this is Hamiltonian, and then you can complete the square. So there's a Coriolis force that acts like the gauge field, and then as a result, also there's a centrifugal force that flattens the original traps. So the phenomenology is the following: that one start with the ideal situation is that one start with a very, very tight trap in all directions, especially in the z direction or both directions, and then you begin to split it, and then the system lock in the lowest state of the three-dimensional trap, and then gradually, gradually flatten out, becomes very flat. And then the flattening of the trap is given by this centrifugal force. Now, certainly, if this guy goes away, then one would have a really faithful representation of the electron problems. But the problem is that when this is getting close to, when omega goes to the rotational frequency close to omega, sometimes one can also make it negatives, and then you will be by accident just killing your sample. So I think that is also one of the difficulties in experiments, because you would be by accidentally losing particles, but that is a technical issue, a non-trivial one. So in the limit of say when these two frequencies are getting close together, that which refers to the criticality, then this becomes a really Landau problem, and the energy levels looks very simple, and then exactly like the Landau level, except that it has a tilt, a linear tilt. The linear tilt comes from the fact that there is a residual centrifugal a barrier, even though weak, but there's a barrier. So that is the single particle Hamiltonian, the energy level that we have. The wave function here is exactly z to the m. Now I should mention the next Landau level, because later on we are going to use it. I think it was also mentioned earlier today. If you're going to go to the next Landau level, the wave function is also not too complicated. That you have to multiply by z. You have to introduce a complex z star. Not everything is not completely analytic, but then there will be a polynomial. The maximum polynomial, the degree of polynomial is m. So if you go straight, and then your angular momentum would be decreased by 1 unit. So these are the structure of the wave functions. Then now let me just first mention the class of bosonic states that we are interested in. Now, why interested in boson, not fermions? I think actually I was baffled why everyone was interested in boson, not yet fermion. I think the answer I get is, well, maybe they have fermion already, and then why don't we study boson? And also for boson, automatically, if I get to the quantum Hall state, then you'll get the fractional. Yeah, you are in a fractional state. So therefore, and then the classes that we're interested in, of course, this is the Loveland form. And then there's another form, which is what I refer to the Farfian state. Now, these zeros and ones are following. That suppose you have lots of particles in the system, and then you just artificially divide it into two groups, and one of them called 0, the other called 1. I mean, this division is completely artificial. And then in each group you form a Loveland cluster, and then you symmetrize it, and that is refers to as the and of course, you can continue to do this for many, many clusters. And then there's the cluster state, and these are the so-called analogs of the precise series in the fermions. But then this is so the simplest one is this cluster. And turns out this cluster state is the bosonic analog of the fermion-Farfian state, and it is a P-wave pairing, is related to the P-wave pairing states. Let me just spend a little time, and I know that there are many experts in the audience, so I ask you for your patience. And now, so this is the I just talk about. Here's a bunch of bosons, and then you suppose artificially divide into two groups, and then the guy. I just color them differently, and then so one of them belongs to the darker one, the other one belongs to the gray one, and then you form Loveland cluster, and then you subsymmetrize it. Now, to understand the structure, further understand the structure of this cluster, now I would repeat one of the simple things that Sento talked about yesterday, that for any symmetric, anti-symmetric polynomials, and they can be written in this form. Now, a polynomial does not have any property except for zeros. So, and then, however, if it's anti-symmetric, that means that if I look at this is function of z1, and then the other one is parameters, and then I must have a 0 when z1 equals z2. So, but then by symmetry, then you have this collection of factors. So this is a very simple to establish. Now, but once you establish this, then one can immediately work out something not entirely obvious. So there is a identity like this. I mean, on the left-hand side, you have this bunch of things, and then it's not quite like Loveland correlated factors, but then the two type of coordinates or particles correlated with each other, and then you have a determinant. And then the whole thing, it turns out to be equal to this. Now you say it might appear to be very mysterious, but then turns out it's not, because what happens that this, even though there's a divergence, but there's actually no divergence, that you multiply the whole thing out because there's a factor here, cancel that factor here. The whole thing is simply a symmetric, a anti-symmetric polynomial of u's. Because this one's symmetric and this anti-symmetric, and therefore this must contain a factor like this. And the same for W has a factor like this, and then you compare the coefficient, and then turns out your match coefficient is 1. So that is it. So this simple fact allow one to come up with now. But the implication of this is the following: that now let me take a look at this state, this cluster state. I divide the system into two groups of a Loveland factor, and then use a Cauchy identity, and then now I can take one power and then use a Cauchy identity to write it in this form. I mean, this one, UV becomes 0 and 1 now, and the determinant. Now, but then this is 0 and 1, basically, now I'm just correlating every particle in this Joshua way in all the particles now. So this whole thing becomes just a Loveland factor for all the particles, independent of which group they are. And then now, because now this whole thing becomes anti-symmetric, and then because the determinant also anti-symmetric in the coordinates, so you can again show that this is equal to this anti-symmetric product times a pair product of pairs. And because the original z's are bosons, but because this object is anti-symmetric, so inside this, so as far as this determinant is concerned, then it looks like an anti-symmetric function. So the bosons are fermionized because of these factors, and it's in the p-wave B-set states. And that is in this sense that the Loveland states this two cluster states is p-wave states. And then you can and there are, as I mentioned, there are higher clusters, and all the cluster states except for the lowest one, which is a Loveland, are all supposed to have, I think from various studies, non-abelian statistics. And we'll come back to that later. Now, so if I want to create these states, then why is it so difficult? And then the reason is two reasons. One of them we have mentioned is extrinsic, just because you need this to be very flat. And you need to be very flat, you need to rotate it very close to here, and then sometimes you make mistakes when there's noise, and then come down, and then you're dead. But on the other hand, there's another problem which is much more serious. That's the problem of Bose condensation. The Bose statistics. This is very intrinsic. The bosons the bosons always want to search for the place where the energy is lowest. And then this, I think I told my students it's like the eye or Zarans are always looking. Whenever there's a place that's a lower energy, they want to condense over there. So what happened is that even though everything is in the lowest Lambda level, the bosons like to come to this state as much as possible, and the result is that it will organize the vortex lattice, and the vortex lattice basically occupy a bunch of states. In contrast, quantum Hall state, you need to spread it out all the way to the very far away. So the question is that how to do that, and then now in contrast, however, the Fermi statistics works for you. The Fermi statistics will naturally spread out. So as a result, at the same rotational frequency, the same kind of structure, it's easier for fermions to become quantum Hall states than bosons become quantum Hall states. Now, so the purpose of this talk is to propose a way to overcome to get around both statistics. And the method proposed is to put together some of the very well-known physics in coatoms, in particular, i.e. the flashback resonance. So by the proposal is that we first create the fermionic integer quantum Hall states on the, well, I will describe to you what do I mean by BCE and BEC size resonance. So we produce some fermionic states first, but in particular in the integer quantum Hall state. And then we do flashback resonance. Now I'll tell you what the flashback resonance is for those of you who are not familiar with it. And then from one side of the resonance to the other side. And the purpose of the flashback resonance to associate particle into pairs. However, we have to go through it not just arbitrarily, but go through it in a way that Debye goes through the resonance at that particular speed, and then which I would talk about the physics of that later. So you do not go through it adiabatically, but go through it at a particular speed. Then then I will show that in this case, then you can make a bosonic Loveland state and the Farfin state during this process, and there are little corrections to the states we designed to make those states. Now let me now talk a little bit about flashback resonance, and let me talk about the physics of it. Let me talk about zero rotation first. I mean, there are no rotations. So in the harmonic trap, you have something like this. Again, you don't even need to look at the harmonic trap. But the wave function is that the two particles interacting with a potential, and then depending on the potential, and then sometimes you can form a bound state. Now the general picture is the following: that you can think about there's a potential here, and then these are the non-interacting energy levels of the, let's say, of a system in free space or in a big box. And then these are energy levels. But then if you turn on the attractive potentials, and then the states will come down, and then when this state will come down to this, so on and so forth. But the last state will return into a bound state. And when the bound state occurs, and then this is the places where it's refers to as the resonance. And in practice, it turns out because of the various atomic physics potentials, then one can actually tune the system through this by just turning a knob by changing the magnetic field. So this is a very convenient way to do it. You change the magnetic field, you can go from one side to the other side. Now I want to there's a jargon in the field, and this thing is referred. This one is referred to as a lower branch. The upper branch is referred to something like all the extended states up here is referring to the upper branch. Now, so I now want to mention this very famous experiment, and this it generated a lot of discussions. Even emotions in 2004. It's the first time is really the first experiment demonstrating pair condensations. So the Marcus is here, and I'm now quoting exactly what is on the paper. This is what you wrote. And this is the paragraph that I had a lot of discussion with Eric at some point in the letter, because initially I didn't believe it, but then later on I realized that actually it is very true. So therefore, let me just back up. So For example, if I start with say a pair particle here, and then I just go through this. Now, of course, if I go through very slowly, the pair particle can go into can form a pair. But the question is, what happens when I go through reasonably fast? Now, why do I want to do that? The reason they want to do that is that I think at that time, then the question is that one is interested in the center of mass momentum of the pair. Now, if I go through a particular speed, and then I think marketing that Mohit Marandiria worked out 20 years ago. So what I would like to point out to you is that there is a process where you can sweep and then you freeze the moment you can collect the particle in associate particle in the pairs and yet not affecting the center of mass. Now this process is very unique in coatoms because it's very hard to do in electrons, because electron Coulomb interactions, to bind conduction electron into pairs or tightly binding pairs, it just is extremely difficult. So now in a quantum Hall state, then what one can do is the following. Again, you can do the problem, and then not surprisingly, for a two-particle system, you can separate out the center of mass coordinate, and then the relative coordinate. Now, and then again, if you go through this Feshbach resonance, so suppose initially you have two particles in the quantum Hall state, suppose it's a far from resonance, and then they're just moving with different angular speed, and you can show that the center of mass, if you go through resonance, center of mass is still the same. Now, however, when I associate a particle into a pair, one has to go away from the lowest Landau level, because when you go down, because in the lowest Landau level, the wave function can only get together, particle can get close to each other at certain distance, but the wave function has a width. So in order to make the very tiny bound wave function, then one has no choice but go away from the lowest Landau level. In contrast, the center of mass can always remain in the lowest Landau level. So there's some point that I want to stress. So now, what does this? So the question that we are going to address is that what happens if I go to sweep the integer quantum Hall state from the BC side of the resonance to the BC. Oh, I forgot. But BC side of the resonance is that the particle hasn't formed pair, and then the BC side they form a tiny bound pair. Now, I am not going to talk about the adiabatic sweep. The adiabatic sweep would be because during the adiabatic sweep, the center of mass would have lots of time to adjust itself, and then there may be quantum phase transitions. So that is not as in contrast, I'm going to talk about the kind of sweep that Giller was using, and then now let's see what happened if I take the. So this is the question. So I start with a first Landau level, second Landau level. Or suppose I start with a system where I have two field Landau levels, up and down spin, and then I start with a system with two Landau level field, but for up and down spin. The question is what happens if I go through over there? Then so in order to understand that, let's look at the integer Landau level first. And then I would like to point out some. Okay. So this is very well known. I suppose that for fully field Landau level, then you have the wave function, the Slater determinant, and Slater determinant again by that theorem is again a polynomial, and then therefore it must contain this form, and then you count the power, and then that's it. There's no more. So this by symmetry has to be all this form. And now if I have two components, both up and down in the integer Landau level, then the wave function is just z is up, w is down. The wave function is this product. Now I would like to point out another identity. The identity is the following. I take this product, and then I'm going to claim that suppose I take one set of zi. Again, I associate this is a one spin up particle. I associate a spin up particle with another spin down particle, but in an arbitrary way. P is just a permutation. So P is any permutations. And then this I claim up to the constant is exactly the same as this. Why? Because again, you can use the theorem before. This is nothing but, again, an anti-symmetric polynomial because I anti-symmetrize it, and therefore it must contain this factor. And I also anti-symmetrize W, I must contain this factor. Again, you count number factor, and then that's all there is. So it must, now, but what this said is the following, that because P is arbitrary, that means that I can, so I can have many grouping of up and down spins now. But no matter the grouping that I make, that the center of mass of this grouping, or the way that I group, the center of mass of this pair that I produce in this grouping will automatically fall into a bosonic Loveland state. So there's an incipient structure, quantum Hall structure for the center of mass of the pairs. So here's a situation. Here's a group of particles, say in the here's these are up and down spin with different color, and then this is one way to group it, and then center mass of this are given by stars. However, there are many different ways of grouping it, and then for example, you can exactly the same configuration, you group it different way, and you have this configuration. However, no matter how you group them, then the center of mass are described by the bosonic Loveland amplitude, because of that identity. Now, so therefore, what happened is the following: if you collapse them by, you could go through a Feshbach resonance in such a way that if the two particles come, they all shrink together, but they all shrink back, and then if the center mass of these pairs remains unchanged, then you once ending up with a bosonic Loveland state. As I said, there are many ways you can do it. So there are which one that we select, then what is selected out is by the camera. You take a picture, the boson, you take a picture, and then you select one of them. And you can also convince yourself that different kind of grouping, because of the fermions, and if I have this grouping and the other grouping, and they are orthogonal to each other, so you immediately go into many different orthogonal Hilbert space, and then when your measurement will pick up one of them, but all of them has the bosonic Loveland correlations. Now, then here is the way to describe the projection process. I mean, so this is just this is the original grouping of the particles. When F is just described the pairing of the particles. If F is 1, then you get back the original Landau level. But if you tie them up into a delta function, and then you get the Loveland state. And the measurement Loveland state will basically measure one of these set of coordinates. Now, okay, well, sorry. Yeah. So one can do it for quasi-particles, and then so let me just get back to one point. When I quoted the statement of Marcus and Debbie and Cindy, and they were saying that when I sweep through the resonance, I may be typically getting 60% to 80%. So suppose you only get 60% and not 80%, and turns out you can also work out the wave function in the process. And then so what happened? I'm not going to go through the mathematics, but what happens at the center? You have the Loveland droplet outside, and you have this extra. One can just show that outside you have this extra particle. That particle that is not didn't form pairs. Now, let's go to the 2 Landau level. Now, question. Yeah.
So I'm a bit confused about the degeneracies of the many-body states on the two sides.
Say again?
So the degeneracies don't match on the two sides, right?
I'm not talking about I'm not changing adiabatically. I'm not doing. That's why I'm not looking at the ground evolution of ground states. I am doing a dynamical process, and I particularly emphasize that the adiabatic process is not we are going to do. But your question is, that's why I say if you do it slowly, you may have quantum phase transitions. But then now I'm going to do the sweep for the 2 particle for the 2. You go to 2, and now for nu to 2, then then you have the wave function, the lowest Landau level. Now I mentioned before that for the next Landau level you have to multiply C star, and then you can show that the Slater determinant turns out to be organized in this form. And then now one way to look at this big anti-symmetrization is that you can symmetrize the up level first, and then symmetrize the first level, symmetrize second level, and then you anti-symmetrize the whole thing. So when you symmetrize the first level, you get the Joshua factor, for the Loveland factor for the first level, and then you get this second Joshua factor for the second level. But for second level, then you have this object. So then this is and then now you totally anti-symmetrize the whole thing. Then now it turns out that now if I have two components, spin up and spin down, so the wave function is just like this. So, and again, well, I should write down an equal sign here. And turns out then, this is the same. I can just write down with this thing is very long. I can just, this is the form of the second lambda level. Then what happened is the following, that in the second lambda level, now again one can generalize the identity. And then here, suppose I take an arbitrary combination, or arbitrary arrangement of up, and then arbitrary arrangement of down. And then again, you can show the identity that you again divide into two groups. And then, because originally you have two groups, right? So you take one group, and then you form a Loveland factor, and then the two and take another group, form a Loveland factor, and then you anti-symmetrize it with respect to this group that you start with. Again, you can show by the same argument, then this identity up to a constant, and you get something like this. So again, what this says is that in a second, if you have two lambda level, if you just look at arbitrarily group the particle into pairs, and the center of mass are already organized into a cluster form, and in particular in the cluster form appropriate for the Fabian state. And then so let me so this is now so here the dark color, let's say the blue color, the dark one, so it says light blue and dark blue represent spin up, and then the light orange and red represent spin down. But then we have this, we have said that we divide into two groups just because there are two lambda levels. That now there are many ways that you can group them in the pairs, up and down pairs. You can up and down pair they can be in the same lambda level, or they can be in a different lambda level. And then again, there are many ways of grouping them. And then again, if you go through I think this again a pictorial way for the nu equals to 1, the previous case. Then you just have a spin up and spin down. You just glue them together. However, if we have a case of both up and down spin, but nu equals to 2, and this is a very schematic. Say this is the lowest lambda level particles, and the second lambda level. I mean, this is I'm just do it pictorially, and then you just then one can glue the particles during the SRIP process, then one can glue the particle in different ways, and then you can have the lowest lambda level tie up with low lambda level, and this is of different lambda level, and the fact that one have a different choice for producing or gluing particle is related to the non-abelian statistics. That so again, I'm just repeating what I said in the so this statement applies to the both single component and two component case, and that is the so no matter what grouping that you take, then the center mass automatically correlated in the bosonic form, and then so in this case, then again you get the projection, and then now in this case, because of this factor of Z stars, and one do not get a pure pair form, or the cluster form, and there's a polynomial because of Z stars, and then okay, then I think for the people in quantum Hall, they know that if you have a polynomial, you multiply something with much low power, and then those are considered to be some either edge excitation, some small excitation systems, but the dominant factor of angular momentum is controlled by this cluster. So so now I am since my time is so the message I like to convey is that the center of mass of the integer quantum Hall states automatically organize themselves in the cluster states, and the projective SWIP, not adiabatic, right, will reveal the incipient bosonic structure of the center of mass, and which is either the Lufkin state. Now the excitations, I haven't talked about the excitations of the cluster states, are therefore connected to those of integer quantum Hall states. I mean, that's something I'm still working on very hard on, and then I think have some favor of Janenja's construction. Now, then the question that Eric may ask is, okay, now suppose you do get this states, but this state may not be. I mean, you go to a BEC side. How do you? But this state may not be the ground state of the system. The ground state may still be a Bose-Condensate. Then what are you going to do? Now, I think the answer to that is that if the system, but I think you have improved the symmetry of system a lot. So if the system is really round, have a high degree, so you can preserve angular momentum. You see, the ground state has angular momentum of order n. This one has n squared. It takes you a hell of a long time to get to the ground state. Now this thing may, so I think the hope is that the angular momentum conservation will preserve you into this state. In particular, for the Lufkin state, it is for Lufkin, one can show that it is an eigenstate of the Hamiltonian. Even though so basically, suppose your ground state is somewhere, but then you are excited state, but you are also an eigenstate of the Hamiltonian. So I think there are some chance for stabilities. So that one can operate on these samples, do experiments, and the experiments I think one is really interested in experiments to detect the anionic characters of the systems to measure the phase. And so I think if one, I think at the moment our community just need to produce one quantum Hall state. I think I would suggest produce a fermionic quantum Hall state. From then, I think once you have a quantum Hall state, then that will generate a lot of activities, and the bigger the better. The bigger the better. So. Thank you very much.
Just need to make a really big quantum Hall state optical gas people. How hard could that be? Questions? Yeah.
Can I ask
Oh, please.
maybe
Hi.
a very naive, simplistic question? Suppose you had the potential to have the appropriate interactions to make your Laughlin state, but the problem is just one of preparation. Could you play the same kind of a trick and make a bosonic integer quantum Hall state from two species?
What do you mean? What do you mean by bosonic integer quantum Hall states?
I just mean one
You mean
Feshbach molecule, if you will, in each of the L states.
But they're bosons.
They're bosons.
The Farfin. Let's see. The Farfin states already. Well, depending on what's the question is what is the filling factor of the bosons? Are you talking about filling factor 1/2 or the filling factor? Oh, filling factor 1/2. But then the Lufkin state is already filling factor 1/2. But then the
integer quantum Hall state is a filling factor 1, so it's not going to work.
The Farfin state has filling factor 1.
I see. So you get a Farfian out of that?
But I don't know whether the kind of state that you have in mind is this kind of, but the Farfin has filling factor 1.
You're starting with a filling factor 2 for the individual particles, which is equivalent to filling factor 1/2 for the pairs. So therefore, you can go from one to the other.
Yes,
But you have to start with filling factor 2 for the with the two. Nu up equals nu down equals 1, which is 2. Equals 2, which is the way the logic works. You have to divide by 4.
Right. Yes, precisely. Yeah. One could also play the game of suppose I start with I associate a nucleus to 1, if I spin up, a nucleus to 2 spin down, then one have more possibilities, and then So
Jason, you said something tricky, and I want to make sure I heard you right. The tricky thing you said is that At any magnetic field, the Laughlin wave function is an eigenstate, although not a ground state. Is that what you said?
Oh yeah, Laughlin wave function is it's not the ground. It's
So
eigenstate.
if you go to what would be...
May not be the ground. May not be
Yeah,
the.
so if you went to nu equals 7. and
Nu
so-
equals
so-
to
and I'm just making a random number
Yeah.
because it was a random choice. And I wrote down a Laughlin wave function of bosons. It would be weird. I could,
But the Laughlin wave function has filling factor of 1/2 by definition.
yeah, that's what I'm trying to get out of it.
So you want.
You said those words.
The reason that the reason that the Laughlin factor eigenstates is because that's all, because it's all at Zi minus Zj. The no two particles cannot come close together, and therefore it quenches the.
Right, so I agree that the interaction
Right.
energy is 0, but it doesn't seem to follow that it's an eigenstate.
Oh, because then all the single particles they have same angular momentum, and then they are. You look at you can. Use eigenstate. You look at it. But the other ones, the one that you mentioned,
Made of Lun Ho.
made of Lun Ho levels, yeah. But the other one that you mentioned, that the difficulty, some of them is that the two particles may sit on top of one another. I think that is the difficulty. Is that then to make it to turn those systems, the eigenstate is a hard work.
But 1/2 is short range is gapped,
Yeah, and.
so it's not a problem. So actually, I fail to appreciate the slide that you had that you said that these are bosons. So even if the trapping frequency and like particle leaving of the system is not a problem, we still have a problem to prepare the Laughlin state in U equals 1/2.
Depending on what you want to if you want to prepare adiabatically, and I think then I think to do it in a sample 10 to the 4 particle or 10 to the 5 particle is dead. However, the way that I suggested is that you don't do it like this. And then you start with the fermion on the fermion side, and then bring it over, and then one might have a better chance to get a bigger. Bosonic state, and then this is the process. One just make it but you just make it. But the idea is to just review what is the incipient structure of the Landau level, which turns out to be exactly this state that you're looking for. And so we are not doing anything. We are not doing equilibrium physics now. But at the end, the state that we have maybe the advantage that have exactly those structures that you have that one's looking for. I mean, exactly. And then the disadvantage may be that why may not be. But the question is that I don't know what disadvantage, but the question is how long lived is going to be. Right? And then I'm hoping and praying that it may be long lived because for various reasons we discuss.
Haven't really thought about this, but if you're trying to do these experiments and you're trying to prevent the cloud from collapsing, can't you just continue to put some kind of perturbation that's rotating? So then you're not going to conserve angular momentum.
By collapsing, you mean losing particles? I mean, like what we talked.
Well, I thought that you were worried about the ground state. If you conserve angular momentum, you have a nice ground state. But if angular momentum, if there's some leakage of angular momentum, then you're going to wind up with a Bose condensate in the center. But why do you need to worry about that? If instead of doing the experiment in some ideal trap, you're doing it in some trap which has some bumps on it, and the bumps are rotating at the frequency you want it to be rotating at, then
so that
angular momentum, you wouldn't, anything that tends to relax angular momentum would tend to relax it to this in the rotating frame, and then wouldn't that help?
I haven't fully understood. Maybe we should talk. I haven't understood exactly what you have in mind.
What you tend to do to rotate these things is you put on something that's rotating, and then you try to put it into a circularly symmetric potential and ask what happens, so you can look at it.
Yeah.
Why wouldn't it just pay to keep your rotating potential on? Make it weak, so it doesn't have a big perturbation, but just a small perturbation, and just keep. So then any collisions and so forth.
No, that is the way that one inject angular momentum into the system by making the trap not axis symmetric.
Why don't you just keep it that way?
That's not, excuse me. That's something. When I talk about intrinsic problem, the extrinsic problem, then I haven't emphasized that. So take this problem. If I let's say suppose if you pump too much angular momentum, what happens is that let me start with it. To go to lower cylinder level, I need to populate a lot of these states.
Yeah, right.
But then at some point, I'm going to populate these states because it go very quickly. One exhaust 10 to the 4 particle would really go up to the, so this one will, let's see, maybe I'm not sure.
I'm willing to stay with a relatively small number of particles. I guess I was maybe misunderstanding what other people were saying about worrying about this, that the ground state is not a Laughlin state, but is a state in which all of the bosons would sit at the origin. But that's only true if you're not pumping it. If you continue to pump it, then
yes,
the ground state could really be the Laughlin state, at least to the extent that you're not losing particles.
Yes, and then I think, but that experiment, yeah, you're right. That experiment haven't been done. I think Eric has, I don't know, 10 years ago, I tried some ways to get into that regime. Basically, it's try to go to a smaller number of particle in the within trap, and but I think my understanding is now the technologies are different. So I think this is also being tried. My talk is subsuming that also failed.
I think probably it's getting late.
Sorry.
So we're going to wrap up the session and thank all 4 of our speakers one more time.